as I mentioned in the previous video, we will need to do vector things with Newton's second law to figure out what's going on in more complicated situations. One thing that is very useful in doing problems like this is to draw a force diagram or free body diagram. Those terms are basically synonymous. They mean the same thing. So it's important to be able to draw what's going on. So now that your drawing skills don't need to be good, but drawing a picture of what is going on with the forces will help you then solve the problem. So we got a boat sailing on the water. There's an upward buoyant force from the water, gravitational force, eastward force from the wind, and a westward resistive force from the water. Draw a force diagram for this situation. So you know how good of an artist I am? There's my boat. And what forces are acting on it? Well, we know there's an upward buoyant force, so we draw an arrow upward for that force, and it is buoyant force, so we can write F subscript B for buoyant force. Right? A gravitational force, which, of course, we know what gravity does. We know that that acts downward. We're going to learn more specifically about gravitational force another day. But we do know that gravitational force is downward. There's an eastward force from the wind. And there's a westward resistive force from the water. There's one more force resistive to the west. Now, that's all that we would do based on what the directions say, but just for instructional purposes, then we can take this diagram and use it to write Newton's second law. We know Newton's second law says net force equals ma, and force and acceleration are both vectors, so we can say net force in the x direction equals mass times acceleration in the x direction. Net force in the y direction equals mass times acceleration in the y direction. And then, based on our diagram, we could write out what's going on here. Net force means sum of the forces. You're adding up all the forces. So we have the force from the wind going to the right. We have a resistive force going to the left. So we can write that. Force of wind, force of resistance. This one's to the right, I'll call that positive. This one's to the left, call that negative. And that would be Newton's second law. And then if I gave you numbers, you could plug them in and solve for that. In the y direction, again, just looking at my diagram, buoyant force up, gravitational force down. So sum of my forces, if I call up positive, I have buoyant force minus gravitational force equals mass times acceleration in the y direction. So if we are able to draw the diagram, then it becomes easier to write our equations because we can just look at our diagram. And then if you have some kind of diagram and you have a force that's going off at an angle, then you know, okay, well, I'm going to need to have one component in the x component in the x equation, the other component in the y equation, so I'm going to need to use some kind of trig function to plug that in. Here's an example with some numbers. A spaceship has two forces acting on it. Gravitational force of 35,000 newtons that acts in the positive y direction. So, gravitational force in the positive y direction. So I guess in this case, the positive y direction is probably toward the closest planet or whatever else it might be. The positive y direction is not up in this case. That doesn't make sense. The gravitational force would be down if we were on a planet. And the thrust from its engines of 32,000 newtons that acts at 17 degrees above the positive x-axis. So these are my axes. 17 degrees above the positive x-axis, that's going to be right here. That's thrust, so I'll call it F subscript T. And we know this is 17 degrees, because that's what we're told. Right? So we have two forces, and then we can, with our diagram, we can write our equations. Net force in the x direction equals mass times acceleration in the x direction. Well, what do we have in the x direction? Gravitational force, that's in the y direction, so nope. Thrust, well, that's at an angle, so it does have a component in the x direction, so we've got the thrust force. And then we think, okay, x direction, well, that component is adjacent to the angle. Since it's adjacent, means we'll use cosine. And I'll just write this as a variable theta for now. That's equal to mass times x component of acceleration. Oh, we don't even need the acceleration. It just says what is the net force. Ha ha ha. Okay. So the x component of the net force, we know, is just e cosine theta. We don't even need to write F equals ma because we're just being asked for the total force. Haha. All right. Then in the y direction, again, we look at our diagram. We've got gravitational force going straight up in the positive y direction. And then this is going partially upward. So we have another component. The y component of that is opposite the angle 17 degrees. So that's that, ft sine theta. And from there we can plug in numbers. The thrust is 32,000 cosine 17. So punching that into the calculator, I get 30601, etc. Store that as x. And in the y direction, we have 35,000 plus 32,000 sine 17. Punch that into the calculator. And we get 44355. Store that as y. And then as always, when we have two components, then we can turn those into magnitude and direction by taking inverse square root of x squared plus y squared for the magnitude and inverse tangent y over x for the direction. These values have 2 sig figs, so we should round this to 2 sig figs, which is 54,000 newtons at, and our angle also has 2 sig figs, 55 degrees, and then we look, okay, positive x component, positive y component, so that's in quadrant 1, which means that angle is above the positive x axis. So the same vector stuff that we've been doing, now applied